In this video we're going to look at the last of binary with maths. We've not finished with binary overall in the computer. As you can see, we've still got characters, images, sound, etc. to go for. But as far as numbers and maths goes, this is the last thing that you really need to know. If your PAT is 6 or above, then I'm going to do some more videos to put this into context and show you how it is used or applied in programming languages such as Python. But if your PAT is 6 or 5 or below, then the questions that will appear on the exam paper will involve binary shifting, and this is the knowledge that you need to know. So let's make a start. What do I mean by binary shifting? Let's first of all see if I can run this presentation for you. Okay, so let's go back to our old model of representing an 8-bit binary number. Most significant bit on the left, least significant bit on the right. The numbers double: 1, 2, 4, 8, 16, 32, 64, 28, 128. That's going to be useful shortly. And here I've got a binary number. Everything is 0 apart from the last one, which I've coloured in red. That is 1. If I perform what we call a left shift, all of these digits here move one place to the left. And what I'm going to do, oh, can't do it on that one, sorry. I thought I was in PowerPoint, then I could edit it. I can't. What we're going to do is move all of these bits one place to the left. So you can see that the 1 underneath the 1 has moved underneath the 2 in the next one down. And all of these zeros have shifted along one place to the left. And this one, which used to be the one underneath the 128, has fallen off the end. That is lost. It's not an overflow error, as if you were adding two numbers together. It does set the overflow flag, but that is lost completely. And what happens, which is what I was trying to do, is that the empty space on this side, which wasn't here at all, we put a 0 in. So if we shift all of these bits left again, this red one now goes underneath the 4. We would get a blank value here, which we fill in with a 0, and another bit drops off the end. That is lost. And the same goes if we shift it again. So I'm shifting for the third time, and the 1 underneath the 4 goes to the 8. We get a blank here, we fill it with 0, and again another bit drops off the end. Left shifting. So let's see what's happened mathematically. We started off with 1. That was the binary number. That's the denary equivalent of that binary number 1. So I multiplied it by 2. So 1 times 2 is 2. And then I multiplied that number by shifting left again by 2. 2 times 2 is 4. Multiplied by 2. 2 times 4 is 8. So left shifting is the same as multiplying by not just 2, but a power of 2, depending on where I go. So if I started off here and I said I want to left shift by 3, then this would go 1, 2, 3 across. Left shifting by 3 would be the same as multiplying by 8. And if your powers are good, you should know that 8 is 2 to the power 3. We will look at that shortly. I can do the same by shifting right. Here I've started off with my value red underneath the 8. I'm going to shift the pattern right. The same thing happens. Blank items here get filled with zeros, and whatever was here drops off the end. That data is lost. So I've gone from 8, moved it along to 4. Can move that, right shift it again along to 2, right shift it again along to 1, and if I right shifted this one again, that 1 would drop off. So let's take a look at what we're doing. 8 goes to 4, well that's the same as dividing by 2. 4 goes to 2, that's dividing by 2. 2 goes to 1, dividing by 2. So right shifting is the same as dividing by a power of 2. So if I started off with 8 To end up with 1, I will have divided by 2 to the power 3. The 3 is the number of shifts that I make. So if I did it by 2 to the power 2, that would be 2 shifts. Well, 2 to the power 2 is 4. 8 divided by 4 would give me 2. 1, 2 shifts. A little harder in division to get it around your head, but that's the way it works. So let's show you what happens to this 1 if we sort of shift it. I've started off with 32, and I'm going to left shift it 1, so multiply 32 by 2, get 64. The zeros get pushed off the end. Multiply 64 by 2, I get 128. More zeros get pushed off the end. Multiply 128 by 2, and that gets pushed off the end, and my result is actually 0. Remember, on an 8-bit computer, so whatever's beyond either side of this, it is not counted. So 128 times 2 is 0. It's incorrect. So we've got to be careful when shifting bits off the end, because we will lose some accuracy in the number that we're using. Normally computers are 16, 32 or 64-bit, and we just don't shift that many times or multiply that much, so it doesn't tend to be a problem in computers these days. But in the old days, this was a big problem, shifting bits off the end. And we can do the same with the right shift. If I start at 4, divided by 2, divide that by 2, and finally divide that by 2, the 1 drops off the end, and I'm left with 0, which is an inaccurate answer. Let's take it. So 4 divided by 2 is 2. 2 divided by 2 is 1. 1 divided by 2 would be a half. Well, I've got no way of representing a half in binary at all, so it's just dropped off. So some accuracy is lost with the data. So left shift means multiply by a power of 2. Right shift means divide by a power of 2. The bit pattern stays the same until it falls off either end. The 1s or the 0s drop off, and then the bit pattern kind of changes. That value is lost forever, and data accuracy will be lost. The result, the number you'll get, will not be an accurate representation of the number. So some care is needed with it. So let's take a look at this one. I've got 101. Here's my bit pattern, 101. Now 101 in binary is 5 in denary. I've put it there, and we're going to look at multiplying only. So if I shift it once, I am multiplying by a power of 2, and I'm multiplying by power 2 to the 1. In fact, I've shifted it 1 place to the left. There's my 1. And you notice that the bit pattern stays the same, 101, and I put a 0 on the end. If I start off with my 5 again, but this time multiply it by 2 to the power 2, I'm saying here, shift it 2 places to the left. So I start off with this pattern, shift that 1 there, 2 places, that gives me 16, as you can see. And move that 1 twice to the 4, and that puts the 1 underneath the 4. And if I was to shift this 3 times, 1, 2, 3, I'd get a 1 under the 32. This one would go 1, 2, 3, a 1 under the 8, and that's the same as multiplying by the power 2 to the 3. Notice that the power given is the number of places that I can shift my value, and it's exactly the same with division. If it's 2 to the power 1, if I'm dividing by 2 to the power 1, I'm shifting right once. If I'm dividing by 2 to the power 2, I'm moving right twice. If I'm dividing by 2 to the power 3, I'm moving right 3 times. So let's see this in maths. 2 to the power 1 is the same as saying 2. 2 to the power 2, or 2 squared as you know it, is 4. 2 to the power 3 is 2 cubed, or 8. So this is the same as saying multiply the beginning one, which is 5, by 2. Well, 5 times 2 is 10, and we can see that here. We've got an 8 and a 2, which gives us 10. If I was to start off with this pattern and multiply it by 4, which is moving it 2 spaces to the left, I would get a 16 and a 4. Add those two together, I've got 20. So 5 times 4 is 20. And finally, the same with moving it 3 places to the left, I'm multiplying 5 by 8, which should give me 40? Well, it has. It's moved the 1 under the 32 and the 1 under the 8, add those together, and I get 40. So that's how multiplication works. The same goes for division, but I'm not going to show it to you. You might want to show me that in your working out. So let's quickly go over it. Programming languages have operators. Now, operators are plus, minus, times, divide, and so forth. But they also have operators that can do shifts, and I'm going to show you that very quickly in a minute. Different languages may have different symbols to do this. In Python, we used two greater than signs, which means right shift or divide. We use two less than signs to mean left shift or multiply. Notice that the arrows point in the direction of the way we're shifting. So in Python we could write 5, shift it to the left 1, which would mean 5 times 2. Remember, 2 to the power 1 is 2. 5 times 2 is 10. We'll have a look at that in a second. Similarly, I can do 5, left shift it by 3 places, and that means multiply it by 8, so I should get 40. So let's check that out in Python itself just before I finish this off. So here's my Python. Let's see if I can get some of this back on the screen. I'm going to do this one first. 5, left shift 1, and my answer should be 10. So 5, there's my left shift symbol, whoops, and 1, and my answer is 10. I'm going to do the same with this one. 5, left shift 3, and I should end up with 5 times 8, which is 40. So 5, left shift 3, and I get 40. And the same goes with division. So if I was to divide 5 by, I'm going to shift it right 2 places, so that's sort of 5 divided by 4. Well, that's not going to really work very well. Let's start with a bigger number. Let's start with this 40. 40, I'm going to move that right. Now 40, if you remember, still the bit pattern 10100. I'm going to move that right by 2 places, so I'm dividing 40 by 4, and that gives me 10. Now that maths might be a little bit difficult for you to take on board. Like I said, once we get to this point, really you're looking at Pat 6 and above. However, I should expect you to be able to shift a bit pattern, not necessarily a number, but be given a bit pattern and say move it 2 places to the left, and you be able to do that. Or be given a bit pattern, and let's take a look here, be given a bit pattern like 101, there we go, and be given a power of 2, and note that that is the amount of places that you're going to move it, either left or right. Multiplying means go left, divide means going right. So that's the end of the maths section. As I said, if it's Pat 6 or above, I have given some videos. There's 4 videos on how to subtract using something called 2's complement. It would be nice for you to have a look at that. I will probably program that also so that you can see it in action. And I'm also going to do a few videos on Python to put all of this maths into context, just like I have done here, where, whoops, wrong one. Somebody's nicked my Python. Oh, no, I shut it down. So that it's all in context for you, so that you can see why we use this, why we need to learn this, and how it's applied in languages. I'll give you some exercises to do, submit your answers, and I will also give you the answers in the following lesson.